Oh, yeah. All right, time to get started. So last class was about methods for solving MDPs, in particular policy iteration and value iteration. And those methods only worked if you have an MDP with a finite number of states and actions, and you know what all the transition probabilities are. Now, today we're going to talk about a different kind of method called policy gradient methods. And these methods are a little bit more straightforward to apply to problems where some of those conditions don't hold. So you can apply these in problems where you don't know any of the transition probabilities and where you're using function approximators, which you would want to do if you have a infinite number of, if you have an infinite state space or a large state space, and possibly you have a continuous action space. So let's first just review exactly what optimization problem we're trying to solve. So in the problem of, in reinforcement learning, we're trying to maximize the expected reward, or the expected sum of rewards over time. And there are actually various different forms of this problem. So let's just review some of the different optimization problems you might write down. So we have the fixed horizon episodic problem, where that means you have a fixed number of time steps, capital T, and you're trying to maximize the expected reward over that time horizon. Then there's an average cost problem, where you care about the limit as t goes to infinity of the sum of rewards. So you care about the average reward, which you can write down as the average, the limit as t goes to infinity of the sum of rewards over capital T. Then we can look at this infinite horizon discounted formulation, where we sum up all the rewards and we multiply them by discount factor gamma to the t. So that means we care about the rewards in the future less than we do at the present. So this would mean, for example, if gamma equals 0.99, then when we care about the 100th reward less than the 0th reward by a factor of 1 over e, or 0.99 to the 100. Or sometimes we look at a formulation where the trajectories have variable length. So sometimes we describe a problem where there's a probability of transitioning to a terminal state, and after you transition to a terminal state, the episode ends. For example, if you have a robotic control problem, you might say that when the robot falls over, you call that the end of the episode. So this would correspond to a formulation where you have a variable length in the trajectories. And lastly, we might have an infinite length trajectories, but the MDP is set up in a way that the sum always ends up being finite. So these are just some different ways you could formulate the policy optimization problem. As it'll turn out, they all yield basically equivalent algorithms. Or the algorithms you use in practice end up being mostly the same. And we're going to mostly focus on the fixed horizon episodic formulation. That means you have a finite number of time steps, and basically all the other formulations can be expressed as some limiting case of this formulation. So I won't go into all the technical details of that, but just wanted to mention that there are these other formulations, but we're just going to stick to the one that'll simplify the math. So we can just describe this formulation a little bit more formally as a certain kind of stochastic process where you sample the initial state S0 from some probability distribution mu of S0. Then you sample the first action A0 from the policy, which is called pi. Then you sample the next state and reward S0 and S1 and R0, and so on until the last time step, capital T. So this process, you can call all the variables you just sampled a trajectory. This is just the process for sampling a trajectory. And we're interested in maximizing this expression that we'll call eta, which is just the expected value of the sum of rewards. Okay, and you can also write it like as a graphical model like this, where you can say that the actions are sampled from the from a distribution, and the transitions, there's another distribution that gives you the state transitions. And as we mentioned before, we're going to, as in the last class, we're going to be talking a lot about policies, and and there are two kinds of policies. There's stochastic policies and deterministic policies. We're going to use theta to denote the parameter of the policy. So that means that theta indexes over the policies. Usually theta is going to be a vector of real numbers. And that just means we have some kind of network that we're going to use as to compute the action, or to compute a probability distribution over actions, and theta just is all the parameters of that network flattened into a vector. So this is actually the way you parameterize policies is completely analogous to the way you do classification or regression. So in classification, if you want to use neural networks for classification, you have a network that takes in the input, for example, an image, and it'll output the probability of the different labels, for example, the different classes of the image. In this case, for parameterized policies, you just have a network that takes in the observation or the state, and it outputs the probabilities of the different actions. So you can use exactly the same kind of networks you'd use for classification in the reinforcement learning setting. For deterministic policies, you can do something pretty similar where you just take the argmax. So instead of outputting a probability distribution, you can just take the action that has the maximal output. And similarly, if you have a continuous, if you're solving a reinforcement learning problem with a continuous action space, then you can use the same kind of networks that you would use for regression. So you have a network that outputs a vector of real numbers, and you can take that to be the mean of a Gaussian distribution. And then you can have the network separately output the log standard deviation of the Gaussian, of these components of the Gaussian. So that's like outputting the diagonal of a covariance matrix. Or you can just say that the covariance matrix is fixed over space, meaning it's independent of the state. So you can just have a separate vector of parameters for this diagonal of the covariance. When we talk, you'll see that in the homework assignment on policy gradients. You'll get to see more explicitly what kind of architectures work for continuous action spaces. Okay, so now let's just now we're going to get into the mathematical derivation of policy gradient methods, or first the description of what we're going to try to do here. So here's the optimization problem. We're trying to maximize expected total reward, which depends on this parameterized policy pi sub theta. And the intuition is, well, there are several different versions of the intuition. So the first intuition is we collect a bunch of trajectories, and then we, some of them are good, some of them are bad, and we try to make the good trajectories more probable. So this is the crudest kind of policy gradient method. And a slightly more refined intuition, or corresponding to a slightly more sophisticated kind of policy gradient method, is to try to make the good actions more probable. So you try to figure out which were the good actions, which were the bad actions along your trajectories, and you try to increase the probability of the good actions. And lastly, there's a class of methods that try to actually push your actions towards better actions. And we're going to talk about that in a later class. So the basis of these policy gradient methods is actually this older idea called the score function gradient estimator, also known as the likelihood ratio gradient estimator. So this applies not just in the reinforcement learning setting, but in general, where you have an expectation and you're trying to compute the gradient of the expectation. So let's say you have a function f, and you have some random variable x, and x is sampled from some known probability distribution, which we'll call p of x given theta. However, we don't know what f is. So f we're going to treat like a black box. So for example, f might be some kind of simulator that does some really complicated calculations, and maybe it's like a physics simulator doing some kind of aerodynamic simulation. So you're not going to differentiate through that or anything, and you don't even necessarily know what's in it. So is it possible to compute the gradient of this of expectation of f without even knowing what f is? But note that we do know what p is. So we control how we're sampling x, but we don't know what f is doing. So the question is, can we compute this gradient estimator? Can we compute grad sub theta of expectation of f of x? And it turns out that we can. And the intuition is what I described on the previous slide, that we're going to sample a bunch of different values of x. Some of them are going to give some of them are going to give a large f of x, and some of them are going to give a small f of x. And we're going to try to make the large f of x values more probable, the good ones more probable. So to derive this, so it turns out that this like rough intuitive statement corresponds to an actual unbiased gradient of gradient estimator of the expectation. So the way you can derive it is you just you write down the expectation as an integral. So that's the integral on top. So we have so we have this expression on top, grad sub theta of this integral. Then we can swap the integration and the gradient, and that turns out to be valid whenever p is a differentiable function of theta. Actually, I think when p is a continuous function of theta. And then we just apply the, so then we just multiply and divide by this probability density p. Then we apply the chain rule here to noticing the fact that grad sub theta of log probability is just grad probability over probability. And then finally, we get this expression at the bottom. So we have expectation of f of x times grad log probability. And this is an estimator, meaning that we can collect a bunch of samples of this expression inside the expectation, and then we take the average of those samples, and that's our estimate of the gradient of the expectation. And it's unbiased, meaning that if we get enough samples and take an average of enough samples, it'll converge to the correct value, or the exact expectation we're trying to compute. Any questions about this?
What's the variance of this estimator like for like real big models, I guess?
Yeah, that's going to depend a lot. So you can calculate what the variance, you can do a little calculation of it, and it gives you some, it gives you a sort of messy expression. It's going to be, let's see, can I say anything that's sort of qualitative about the variance? You want the magnitude of f to be as small as possible. That's one thing. Yeah, we're going to talk about variance reduction later, so maybe that'll give some intuition. OK, so yeah, our gradient estimator is this expression g hat, which is just f of our sample times the grad log probability. Yeah, OK. There's another nice derivation of this estimator that's worth being aware of. So you can write down the importance sampling estimator for the expectation, where we so basically we have the thing that makes this gradient a little tricky to compute is the fact that the parameter appears in a probability distribution. So with the importance sampling estimator, we can write down an expectation under one distribution using an expectation from another distribution. So we have first we have the distribution with parameter theta, and we write it in terms of the distribution with parameter theta old by introducing this ratio of probabilities. Then now our parameter only appears inside the expression, not in the distribution. So we can just swap the derivative and the expectation because of the linearity of expectation. So that's what we do here. Then we okay, then we want to just evaluate that expression at theta equals theta old. So that's the point where we're trying to evaluate the gradient. And then we just note that this can also be written as the grad log probability. So you can either write it as grad probability or grad log probability. Okay, and there are a bunch of different. This is important, so that's why I'm going through it in a bunch of different ways, because this estimator is sort of the basis of a lot of other things we want to do. So, okay, I mentioned this intuition that let's say f of x measures how good the sample is. We want to, if we move in the direction of g hat, that's our gradient estimator, we're increasing the expectation. So the intuition is, if you look at this expression, if we move in this direction, it'll push up the log probability of the sample x sub I proportionally to how good that sample was. So we're pushing up the log probability of the good samples by a lot. And this is valid even if f of x is discontinuous or it's unknown, it's just this black box, or the sample space is discrete. So here's a little meme. You can have a little physical intuition too. So let's say f of x is this linear function and p of x is this density drawn here. You can imagine that we're trying to push up the log probability of each sample proportional to f of x. So it's like you can imagine that p of x is like a metal plate, and we're trying to push up on it at each of these samples. So clearly, depending on the slope of the density, we're going to push it in one direction or the other. So we're pushing up on it really hard where it's sloping downwards. So that's going to end up trying to push it to the right. Okay, now we just went through this general estimator, which applies to gradients of expectations, but not necessarily in the reinforcement learning setting. And we can straightforwardly just plug in the probability distribution involved in reinforcement learning, and we can get an estimator, gradient estimators, which will allow us to optimize policies. So in reinforcement learning, we're interested in optimizing this expectation of the total reward of a trajectory. So we're going to write that with capital R, and tau is going to denote a trajectory. So we care about gradient of expectation of reward, and just using our score function gradient estimator, we know that this can be computed using by taking the expectation over trajectories of grad log probability of the trajectory times the reward of the trajectory. So now we just need to figure out what's the log probability of a trajectory. So that means we just have to write down the chain rule of probabilities. So we get a product over time of, if we just go back and think about the stochastic process for trajectories, you first sample the initial state, S0, then you sample the first action, then the next state, then next action, next state, and so on, all the way until time step t. So that ends up turning into a product of probabilities where we have probability of the initial state times probability of all the actions and all the state transitions. And so if we then when we take the log probability, it turns this big product into a sum, and we get then when we take the gradient. So now we take the gradient with respect to the policy parameter theta, and now the magic thing that happens here is all of the terms that we don't know drop out. So basically the only function that we really know here in this big product of probabilities is we know what the policy probabilities are, because we define the policy ourselves. We define that this is some kind of neural network with known forms. So we can take the analytic derivative of this log probability. We don't know what the transition probabilities are for this MDP, and we don't know what the initial state distribution is. But we can still, okay, so it looks like we're in trouble if you just look at this expression here. But then when we take the gradient with respect to the policy parameters, all of this stuff that we don't know drops out because it doesn't depend on the policy parameter theta. So now all we're left with is the sum of we're left with the sum of grad log probabilities of the actions, which we know. So then just plugging that into our score function formula, we get that the gradient of the expected total reward is just the expectation of total reward times the gradient of the log probabilities. I mean, you can switch the gradient and the sum. So people usually write it as sum of grad log probabilities, but I just wrote it as gradient of the sum of log probabilities. Any questions? Okay, so, and just going back to this previous intuition, what we're doing here is we're sampling a bunch of trajectories, and then we're taking the good ones and we're treating them like supervised examples in a classification/regression problem. So if you just look at this objective function we have here, it's like we're maximizing the log probability of these actions. And just think about a classification problem where someone gives you a bunch of labels and you're trying to maximize the probability of those labels. So that's just like what we're doing here, except in reinforcement learning, no one told us what the correct actions are. So what we're doing instead is we're saying that the trajectories with positive total reward, we're trying to maximize those. We're trying to maximize the probability of the ones with high positive total reward. Okay, so that was the crudest possible formula for the policy gradient, and it's crude in that it has high variance. It'll turn out that it has high variance, and we can reduce the variance by just recognizing that certain terms are zero in that big expression. So the first thing we can do is use the temporal structure a little bit to get rid of some terms which will turn out to have expectation 0. So the previous slides gave us this formula where we have sum of rewards times sum of grad log probabilities. I mean, intuitively, this isn't necessary. This is a sort of bad formula because we're not trying to do any credit assignment. You might have a really long trajectory, and half of the actions are going to be good, half of the actions are going to be bad. But we're pushing all of the actions. We're either calling all of them good or we're calling all of them bad. Basically, we're not trying to do any more fine-grained analysis of which ones were good and which ones were bad. So we can do a little better than that. So first notice that we can go through the previous argument and derive the gradient estimator for the expectation of a particular reward term. So here we're looking at r sub t prime, and we're trying to compute the gradient of the expectation of that one term. And here, so we go through the exact, go through the exact derivation with the score function gradient estimator, and we have the expectation of this random variable times the grad log probability of all of the actions preceding that reward, because the actions after that reward don't affect it at all. So that's, we get this expression, and then we sum this formula over time steps t, or time steps t prime. What we end up with is so we can write, so if we just sum over t prime, we get this formula on top where we have this sum on the outer sum where, oh, this should say t prime. So sum over t prime, rt, so we have reward times sum of log probabilities of previous actions. So so this is like whenever we get a reward, we're trying to boost the probability of the previous actions by proportionally to that reward. So if it's a big reward, we're going to try to boost all the probability of the previous actions. Or in this formula, we can just rearrange the sum, because if you look at this sum, it's just got, if we expand it out, we've got any kind of, we've got reward times previous actions. So if we just rearrange it to have the actions as the outer loop, then we have log probability of action times sum of future rewards. So that means for each action, we're looking at all the future rewards and we're boosting the probability proportionally to what the future rewards are. we can further reduce the variance by introducing what's called a baseline. So the idea here intuitively is that we only want to boost the probability of an action if it was better than average. So instead of trying to, let's say all of our rewards are positive, then using the previous formula, we're trying to boost the probability of all of our actions because we're always multiplying log probability times some positive sum of rewards. But we really only want to boost the probability of the better than average actions. So what we can do here is subtract out the expected sum of rewards, and that way we'll only be boosting the probability if the rewards were better than average. So a near optimal choice of this baseline is just what's the expected sum of rewards given state S sub t. So this, I should say, this expectation is conditioned on S sub t. And why do we want to, I mean, why is this going to have lower variance than why is this going to have lower variance than than when we don't use the baseline? Well, you can go through the whole calculation of what the variance is, and you find that the optimal baseline is not this. It's something a little more complicated. But the intuitive reason is that we're trying to, what we want to do is decrease the magnitude of this term as much as possible. So if all of these terms, if we have baseline equals 0 and all of our rewards are positive, then it's like we're trying to boost the probability of all actions, and just some of them are getting boosted more than others. So those are the ones we end up increasing the probability of. But we have all these, we have all these other. Let me go back a step. So intuitively, the reason why the baseline reduces variance is because it decreases the magnitude of this expression right here. And so we're multiplying, like we're taking so I told you that this expression is, this has the same mean as without the baseline, and I'll derive that shortly. So if two expressions have the same mean, then the one where the mean of the square of the thing inside the expectation is smaller, that one has lower variance, because the variance is just the expectation of quantity squared minus the expectation squared. So we're just trying to make this quantity inside the expectation as small as possible in magnitude. So if we subtract out the baseline, we're going to make it smaller. Yeah.
So is B just like a control variable, basically?
Yeah, you can also derive it as a control variate. That's right. Yeah. OK, that was a sort of rough explanation. OK, so why is this? This is unbiased for any choice of B. And that's pretty straightforward to derive by just swapping, by just writing out the expectation and moving some terms in and out of the expectations. So using the law of iterated expectation, you can move around the expectations and derive this. If we have extra time, I'll just show the derivation on the board. OK, so now we can get more variance reduction by introducing a discount factor. So remember that the discount factor appeared in our discussion of policy gradient, of policy iteration and value iteration, where we were just using it because otherwise we might have an infinite sum of rewards, and so our objective would be unbounded, or our value function would be unbounded. And also, to make all value iteration converge, we needed to introduce this discount factor, because otherwise it wasn't going to be a contraction. So we're also going to introduce the discount factor here. And it turns out to be very useful empirically to make policy gradient methods work, to make them more sample efficient. And what it's doing is it's ignoring delayed effects between actions and rewards. So what we're going to do is instead of using the total return, which is the sum of rewards after time step t prime, or after time step t, we're going to use the discounted sum of returns, meaning that we multiply by this discount factor, gamma to the t prime minus t, which means we look at how far into the future the reward happened, and we multiply, we shrink it by this discount factor. So this is the time, this t prime minus t is the time difference. So this is saying that if there's a big time difference between the action and the reward, then you want to shrink you want to ignore that reward more. So the discount factor acts like it acts like an effective time horizon. So for example, if the discount factor is 0.99, then 100 time steps later, we're shrinking the effect of this reward by a factor of 1 over e, because it's 0.99 to the 100. So, okay, and now when we want to introduce a baseline, we want it to be the expectation of the discounted sum of rewards rather than the undiscounted sum of rewards. And again, that's to make this term inside the parentheses have as small variance as possible. So we want to make this term, we want it to have as small magnitude as possible, so we want it to have mean 0. And that's why we're going to set the baseline to equal the discounted sum of rewards. Okay, so that's so we've just been talking so far about estimating gradients. So now it's time to actually turn that into an algorithm. So what we're going to get can be called the vanilla policy gradient algorithm. And the way it works is so you do a bunch of batches. That's iteration is 1, 2, 3, and so on. And each batch you collect a set of trajectories by executing the current policy. At each time step in each trajectory, you compute the return, which is the discounted sum of future rewards following that time step in the given trajectory. Then after computing the return, you compute what's called the advantage estimate. And that's just return minus baseline. So that's an estimate of how much better was that action than the average action. Then we refit our baseline function. So remember that we wanted our baseline to be the expected discounted reward. So I mean, we wanted it to equal the discounted return. So now we're going to refit our baseline function to make it closer, to make it estimate that better. So this is just a least squares. This is just going to be least squares or nonlinear least squares. So we might, for the baseline function, we might use a neural network or a linear function or various things. But all we have to do is solve this least squares problem. Then we're going to update the policy. And to update the policy, we compute the gradient estimator, which we went through before. It's just the sum of the terms grad log probability times advantage. So that's our gradient estimator. How do we update the policy? We just plug that into a stochastic gradient descent algorithm, either SGD, or you can plug it into a fancier algorithm like Atom, which will rescale, which will introduce a diagonal rescaling.
How many trajectories do you usually sample to get like pretty good variance?
It'll depend on how long the trajectories are and how complicated the problem is. I mean, how many samples you need to get a good gradient estimate. And usually usually you can have a noisier gradient estimate if you shrink the step size. So it's hard to give a good answer on how many trajectories you should take. For any number of trajectories, for one trajectory, you can find some reasonable value of the step size such that it'll still work.
But you can also parallelize, I think, that step, right?
Yeah.
Okay.
Yeah. So if you parallelize, then you can usually get a lot of trajectories and take a big step. Yeah. Now here's just a note about how to implement this in practice. So a lot of textbooks and introductions to policy gradient methods tell you that the formula is like grad log probability times your advantage estimate. So then that suggests that what you should do to calculate it is you should compute the grad log probability at every time step and scale it by the advantage estimate and add those all together. But nowadays, we usually do neural network optimization using automatic differentiation packages like TensorFlow. So if you want to implement policy gradient methods with a library like TensorFlow, what you do instead is you implement this loss function, which just looks like log probability times the advantage. And that has the intuitive interpretation we described before as this is like a supervised classification problem where you're using the advantage as whether or not this is a positive or negative example. So we can call that the surrogate function, the surrogate gain function. And then you just differentiate that to get the gradient estimator. And the nice thing about this way of doing things is we can also introduce the value function update into the same calculation. So recall that we're trying to solve this nonlinear least squares problem for the value function. So that if it's nonlinear, then we're just going to, then it makes sense to just optimize the value function with gradient descent. And what we can do is just optimize the policy and the value function at the same time. So we can just write down a loss function that involves our policy surrogate term plus the value function fit error, and we can compute the derivative of both of these terms at the same time. The only caveat here is that on the policy term, we only really want to take one gradient step on this term, because if we take more than one gradient step, it doesn't necessarily make sense, because this expression this expression only gives us the policy gradient estimator if we sampled the actions using the current policy. So if we got our actions and our advantage from another policy, then if we take the derivative of this, loss, it's not necessarily computing anything sensible. So you really only want to take one gradient step on this loss function. You don't want to do multiple steps on it. I mean, if you just optimize this thing to convergence, it's going to try to drive the probability of all of the positive advantage actions to 1 or to infinity if it's a continuous action space, and it's going to try to drive the probability of all the the actions with negative advantage to 0. So clearly it's not going to do the right thing if you optimize this objective for many steps. So it only really makes sense to take one update step on this objective. Whereas for the value function, it makes sense to do as many. It's just a nonlinear regression problem, so you might want to do more than one step on the value function. So that's why I want to add this as a caveat that you might not want to optimize them both at the same time. But in practice, what we're going to talk about in a future class, probably next class on policy gradient methods, is you can write down a slightly different objective here that actually is sensible to optimize for as many steps as you want. So which like avoids this problem that I just described, that this is trying to, if you look at this objective, it's just trying to drive the probabilities to be either 1 or 0. Yeah?
Are you assuming that the same weights theta are used to parameterize the value function?
Yeah, so optimizing these things together would only make sense if you have some weights parameters that are shared between the policy and the value function. But that's actually, so this is used in certain modern techniques like A3C, which I'll mention shortly. So it sometimes helps to share parameters between the policy and the value function because it'll improve your sample complexity, because sometimes like learning the value function causes the policy to represent good features, which will then be useful for the policy. Yeah. If you don't have if there's nothing shared between them, then this isn't going to do anything for you. Then this is useless. Any other questions? Okay, so now we can actually take another view of these policy gradient formulas, which use value, where we consider value functions instead of just considering these empirical returns, meaning the sum of future rewards. So let's just first review what the value functions are that we're going to be considering. So we've got the Q function, or the state action value function. And this is just defined as the expected sum of rewards conditioning on the first state and the first action. And then we've got the state value function where we condition on just the first state. And we can also write down the advantage function, which is just the Q function minus the value function. And that's telling you whether action A is better or worse than the average action that policy pi would have sampled. And remember that a few slides earlier we talked about the advantage estimator. That was actually just an estimator of the advantage function that we just mentioned right here. So we can plug those kind of value functions into our policy gradient estimators. So recall that this is what the formula looks like for the policy gradient estimator that introduces a discount factor. And using a value function, we can derive a new set of formulas. So I didn't show the derivation for these because it's not fun to look at a lot of calculations on slides. But so here's so we can write it. First of all, we can write it in terms of the Q function. So here we have grad log probability times the Q function. And this is like the formula we showed earlier where you're taking grad log probability times the sum of future rewards. But now we're taking the expectation of the sum of future rewards. So this is like a lower variance version of the formula we derived previously, where we replace a certain expression by its expectation. And then by subtracting out the value function, we can get, so by using v pi as our baseline, so we can replace q by q pi minus v pi, and then we get the advantage function here. So this is just saying that we want to increase the probabilities of the actions that have positive advantage. And lastly, we can approximate this expectation by introducing a discount factor. So the idea is that the advantage with discount factor equals to 1 is approximately equal to the advantage with a lower discount factor, like 0.99. And that's true under the assumption that the effect of an action is washed out over time. So we can ignore the rewards that are delayed that are a long time delay from the action. So when you think about the discounted return, it's ignoring these time delayed rewards. So under the assumption that we can ignore these, then this is a good approximation here. And if you're interested, I recommend just going through the calculation that shows that all these different undiscounted policy gradient formulas are the same. It's pretty easy to derive these things. You just have to split up the expectation into a bunch of different pieces, like expectation over action 1, expectation over action 2, and so on. You use the law of iterated expectations, and then you can move some terms in and out of the expectation, and you can derive these formulas that way, and it's not that hard. Okay, so what we're doing with all of these formulas that we showed previously is we're just plugging in advantage estimators for the correct discounted advantage function. So that's what we were doing when we took sum of discounted rewards minus baseline. And all of these advantage estimators are going to have the form some kind of return minus the value function. So let's just go through this a little bit more precisely. So when we introduced this baseline before, and what the baseline was doing is it was accounting for the effect of the past actions. So we're trying to figure out if a given action is good. So we subtract out the value of the current state, which depends on all the past actions. So now what we're going to do is try to use the value function to remove the effect of the future actions from our returns. So we can write the returns in various different ways using the value function. Here's the estimate of the returns we were using before. This is just the definition of the discounted return. So it's the discounted sum of rewards. What we can do is we can replace part of this sum of rewards by the value function, the state value function v, or an approximation of the state value function. So here we're just replacing this whole sum starting at t plus 1 with the state value function. Or we can replace we can start at r sub t plus 2, and we get this expression, and so on. So we can take different time horizons where we replace a certain part of this infinite series with the value function. And these will have different amounts of variance, because if you look at this expression depends on all of the future actions. So you're introducing variance at all of the time steps after t, because all of the random actions your policy samples are introducing some more variance. Whereas this term only has variance due to the first action a sub t. And if we subtract out the baseline, or the value function at the current time step, we can get estimators of the advantage function. So that's what we're doing. So we subtract out the value function of the current time step. And it turns out if the value function v is exactly equal to v pi, or v pi with discount gamma, then these expressions are all unbiased estimators of the advantage function. But if v is wrong, if it's not equal to v pi, then these give you biased estimators. And obviously, this one is going to end up, well, it's not obvious, but this one is going to end up being less biased than the one on the top. Okay, so this, so it's going to turn out that the if you use this estimator in a policy gradient formula, it's going to give you high variance but low bias. And if you use the one on the top, it's going to give you low variance but high bias. Yeah.
So do you just keep another neural network to parameterize v, or how do you actually compute that when you need to?
Yeah. So you need to have another neural network that parameterizes v. That's correct. The question. Oh yeah. Someone on Reddit was asking to repeat questions. So the question was, should you use another network to parameterize v? Yeah. That's what you should do.
But v itself has an expectation in it, right?
So v is approximating an expectation.
Yeah.
So v, we want v of s to approximate expectation of, let's say this is s sub t. We want it to be expectation of r sub t plus gamma rt plus 1 plus dot dot dot. So we're going to solve nonlinear least squares problems to minimize the error here. Yeah. And the idea is that this expression here is really noisy. So if we actually had a good approximation of the expectation, we could reduce the noise by using v instead of using the noisy estimate. On the other hand, it might be just as hard to learn v as it is to learn the policy, so it's not going to help us to plug in this approximation, and it's going to introduce bias. So I said here that the advantage has, I made this claim that this first expression has high bias and the last expression has low bias. So that's not totally obvious given the formulas written down here. But actually, if we go back to the previous slide where we're looking at estimates of the return, then it's pretty clear that if we look at these as estimators of the Q function, or if we look at these as estimators of the expected return, the first one has high bias and the last one has low bias, because the last one doesn't depend on v at all. It doesn't depend on our approximate value function v at all, whereas the first one is totally dependent on our approximate value function. So if v is bad, for example, if v is 0, then the first one is a really bad estimate of the return, and the last one is still a correct estimate of the return. And these you can, so the difference between this slide and the next slide is just we're subtracting out a baseline in the next slide, and the baseline doesn't affect the expected value of the policy gradient. It only affects the variance. So the difference between these two slides is only variance, and it's clear that the this top expression for the returns has way higher bias than the bottom one. So that's why on this slide, the top advantage estimator is going to give you way higher bias when you plug it into a policy gradient formula than the bottom formula. Yeah, so it's not necessarily strictly correct to say that this a hat sub 1 has low variance, but it's correct to say that when you plug it into a policy gradient formula, then this statement is true for the policy gradient estimator. And if you use some intermediate value of k, that gives you an intermediate amount of bias and variance. And there's actually a connection to model predictive control, which was in some of the previous lectures, which is worth noting. I'm not going to go into it formally, so the idea is that what do we do in model predictive control? We look at a finite horizon problem with t time steps, and we compute all the optimal policy at each of those time steps, and we take the optimal action at the first time step for that short horizon problem, and then we replan it at the next time step, and so on. So we always solve a problem with time horizon t each time step. So the way we can think about that in terms of Q functions is we can compute a Q function, a finite horizon Q function, which we're going to call Q star time step t. And we're going to take the max over actions of that optimal Q function. And the horizon, using a finite horizon, capital T, is basically the same thing as using a discount factor. It's just a question of whether you use a hard cutoff for the time horizon or whether you use a soft cutoff, which is a discount factor. So it's like, so what MPC is doing is it's taking the discounted value function, the optimal discounted value function Q star, and it's choosing the optimal action according to Q star. So here Q star just means, remember we were talking about optimal policies in the previous class, and V star was the value function of the optimal policy. Q star is defined analogously as the Q value that you get from the optimal policy. Okay, so that's MPC, what MPC is doing. Discounted policy gradients, we showed in the previous slide that it's equal to the Q value times the grad. It's equal to some expectation involving Q function times grad log probability, where we have a discounted Q function here. And this expectation is only going to be 0 if all of the probability mass is at the best action, the action with the highest Q value. So that means that we're taking we're taking the policy that looks like pi of a given s equals 1 if action equals arg max of q pi gamma, and 0 otherwise. So this is like when you this ends up meaning that we have a the Q function is a fixed point of the Bellman equation, because we have so if we have if we had a suboptimal policy, then when we take this argmax, we're going to get a different action. So anyway, if we have the policy gradient equal to 0, that means we have a policy where the action is always just the argmax of the Q function, And that means that the Q function must be an optimal Q function. So that means that we must have Q pi gamma equals Q star gamma. And so that means when the discounted policy gradient is 0, that means we're doing the same, that our policy is doing the same thing that MPC does. So yeah, that's sort of a rough explanation, and I didn't go. It'll take a little bit more of a argument to show the details here, but hopefully you get the overall picture. Any questions? All right. So now I'll just show a couple of applications that have been. Well, here's one nice application of policy gradient methods, which is kind of one of the earlier nice robotic demonstrations of policy gradient methods. So this one is from sometime in the 90s from Russ Tedrake. Let's see. So here's a video of it. So it's this kind of the paper had a nice title called Learning to Walk in 20 Minutes, and so they had this robot which actually is kind of mechanically designed so that it passively sort of walks, but then they tune the parameters of the walking controller using policy gradient methods, and you can see it walking right here. So that's a nice classic application of policy gradient methods. A recent paper that sort of popularized these methods a lot and basically popularized the vanilla policy gradient method again was called, this paper cited at the bottom, Asynchronous Methods for Deep Reinforcement Learning. The asynchronous aspect actually doesn't really matter for the performance, it's just a speed thing. So it doesn't actually affect performance at all. But the algorithm, they described a version of the policy gradient algorithm, the vanilla policy gradient algorithm, which is very practical for using recurrent neural network policies and using neural network policies in general. So it looks like here. It looks a lot like the vanilla policy gradient method we described previously, but it's using a finite horizon estimator. It's using finite horizon estimators of the value function. Or of the advantage functions. So the way it works is first you have the agent act for t time steps, where t is some arbitrary time horizon you choose, which isn't necessarily the length of the episode. So for example, in the paper they used 5 time steps, and some other papers used 20 time steps. So then at each time step t, you use that short window to compute the returns and the advantages. So you compute the return, which means the sum of all, the discounted sum of rewards going up to the last time step. And the advantage is just that return you computed minus the state value function, which is approximated by a neural network. So they use neural network policies where the network outputs the policy probabilities and also the value function. So you have a network that has shared parameters between the policy and the value function. So then this return r hat is just the target value function in a regression problem, and a hat is the estimated advantage function. And then what you do is you just compute, you update your network, which is the policy and the value function, by computing the gradient of this expression, which adds together the surrogate we described previously, log probability times action, and the value function fit error. So that way you're updating both the policy and the value function at the same time, and they share parameters. And then you can plug this gradient estimator into a stochastic gradient descent algorithm. And they got some very nice results with this algorithm, even though it's a pretty simple algorithm that people previously thought had really high variance and wasn't going to work on any hard problems. They got nice results, like they got this they learned a policy for navigating in this 3D maze where they're collecting these apples. So the policy just has to walk over towards the apples, but it seems to walk nicely and coherently. Let's see. And they also got some pretty strong results on Atari, which is a pretty has become a pretty good benchmark domain. This plot didn't come out very well. So on the x-axis we have training time in seconds, I think it is. Let me just make sure I'm telling you the right thing. Oops. Oh, training time, I mean hours. So let's see, can you see it better now? Yeah. So we have, so here they're just comparing a bunch of algorithm DQN. This is a Q learning variant, which we'll talk about later, and you'll implement on the next homework. And also SARSA, which is another sort of Q function related algorithm. So they're comparing those to A3C. So A3C is able to learn pretty fast, where you have they're using 16 cores in these experiments. So just using a CPU machine. This paper was sort of about like both how to set up the algorithm and how to do it, and how to do the parallel computation, how to do it in parallel. So using a 16 core machine, they were able to learn pretty fast. Well, it's actually not that fast. It's 4 hours to learn Pong. So I think it's actually it's somewhat comparable to using DQN, the Q learning algorithm, which you'll learn about soon. But I guess the advantage here is that it's a different kind of parallelization, and they were able to use CPUs instead of GPUs, so it's less total flops. So this was this was the results on Atari. That wraps up the lecture. Just as a few places where you can read a little bit more about these kind of methods. There's a nice, my friend Andre has a nice blog post about policy gradients, which I recommend checking out, just to get an intuitive picture of them and see some of the research results from the literature. This is the Williams paper is sort of the classic paper in the reinforcement learning literature about policy gradient methods. It actually has a lot of ideas which were later rediscovered. So I mean, the notation isn't very, it's pretty different from the modern notation, and I think the notation is a little bit unwieldy, but the paper has a lot of nice ideas in it. So, and then this is also another, this was also another paper that's that sort of had some nice analysis of policy gradient methods in the reinforcement learning setting from Sutton and colleagues. So yeah, if you can check out, my thesis also has an introduction to policy gradient methods. So if you want to see the derivation with all of the manipulation of expectations, you can find it there. And here's the A3C paper also. I feel like it has a nice simple rundown of a lot of like practical things you might want to do with policy gradient methods, and also sort of hints at the connection between those, how similar the policy gradient methods are to some other reinforcement learning algorithms. So I recommend reading that paper, looking at all the appendices, all the plots in the appendices, which are pretty interesting, where they like vary the parameters. All right, that's it. Any questions? Uh-huh.
Why was it called actor critic in the A3C paper?
Yeah, so actor critic is a name for methods that involve learning a policy and a value function at the same time. So that's basically all it means.
Okay.
I think it's kind of it's a little bit convoluted. It's a convoluted piece of terminology because really it's just it's a policy gradient method with some variations, with some other techniques for variance reduction. But yeah, that's what it means. Oh, the question for all the people watching at home is, why is it called actor critic in the title of this paper, A through C? Other questions? All right. See you on Wednesday.
So in the baseline thing, right? It seems that this baseline affects the gradient directly. So when you adjust the expectation, is adjusting the expectation of the gradient, right? So like, how does that help? Like, is it helping optimization, directly, or because it seems that many papers use this kind of idea?